Topological sorting, and why do we need a DAG for topological sorts? So topological sorting is a kind of ordering in which ordering of what? Ordering of the vertices of a graph in such a way that if there are two edges, and these are directed edges because we are considering DAGs, directed acyclic graphs. Now if there is an edge between u and v, it should be such that u should always be before v in that linear ordering, whatever linear ordering we'll be giving out, right? So for example, if this is my graph over here, what I can say is both of these are valid, because at every point if we see 1 comes before 2, there was a edge between 1 and 2, 3 comes before 4, and 5 comes before 4. In our linear ordering also 5 comes before 4, such that this is the valid case. Now if we come to why does it have to be a directed acyclic graph? Directed because it needs to be directed. We can prove it that if it was undirected, what happens is there will be a 1 to 2. If there is an edge, then 1 to 2 is an edge, and then 2 to 1 is also an edge in the bidirectional graph. We can consider it that way. So this will be 1 to 2 over here. Yeah. So over here what we are saying, that if there is a u comma v and we need that u to be before v always, then we are saying that 2 should be always after 1 according to point 1, but according to point 2 we are saying that 1 should be after 2, which is not possible, right? Like both the things are just contradicting each other. So by contradiction we prove that we need directed graphs. Now why do we need acyclic graphs? So suppose if there was a cycle, again we face the same issue that before 3 we need 1 to get completed, and even after, for 1 to get completed we need 3. So 3 has to come afterwards also, and 3 has to come before 1 also. So cycle should not be present. This is a contradiction, so hence cycle should not be present. That is why we need DAGs. Now how to solve it? What is topological sorting? We got it. Now how to solve it? There are obviously two ways, either DFS or BFS, general traversals. So it is just a modification of those traversals. We just have some storage element over here, which is the array of the vertices in some particular ordering. That is the only addition over the traversals that we are doing over here. Now how the traversals will look like? Now DFS is a bit non-intuitive, I would say, for me, and BFS is more intuitive for me, because it is how the topological sort meaning arises, right? So it is like level wise traversal. After some dependencies are resolved, only then we can go to the next level, and so on. So now coming to BFS implementation, it is also known as Kahn's algorithm. Now in the Kahn's algorithm, a bit of modification if we do, we can also see that if we just give any graph to it, be it directed acyclic or acyclic graph, we can even check if there is a cycle. So how can we check? The algorithm is such that the function will itself return a empty array of topological sorted objects, empty array, or else the length will not be equal to the number of vertices. So in our linear ordering also, all the nodes of the graph should be present. If it is not present, we can just say that it is not a valid topological sort. So only one case arises where there cannot be a valid topological sort if it is not a directed acyclic graph, which means that there is some cycle 100% present in that graph. Now this was the thing. Now coming to the code, first of all, what do we need to do? Over here we have to consider in every case what is the integrity of each of the vertices. Now why do we need integrity? We need to first identify from where do we need to start. it is like a multi-source BFS only, but that multi-sources to be found out has to be on the basis of the in degrees. Now we know that one should come first in our first level, right? This is like level order traversing. Why one should come first? Because over here the in degree was 0. Now considering the in degrees, first we'll calculate the in degree from the graphs. How do we calculate? Every U to V pair, we add an in degree to V, and at last we will have at least one value of U wherein it does not have any in degree itself. It will be 0. So for such values we push it into the queue and we start our multi-source BFS. It is not exactly multi-source, but it is kind of level order only BFS, normal BFS. Because like multi-source BFS and level order would be like, if there are n number of nodes, right, for all those nodes we calculate first, but we do not need a level order kind of a thing. We are going in a BFS term level wise only, but we do not need to store that level context. So that is why we can just keep on adding to the stack, adding to the queue and then removing from the queue one by one without taking into consideration what was the length of that queue for that particular level. We do not need at each level how many nodes are there. We just need that for those nodes if there is some other node in the next level. Now we can see that we have just declared in degree, and then we calculate the in degrees on the basis of the in degrees. If it is 0, we push it into the queue first. Now we know that the queue won't be empty, so it will go into the while loop. Now when it goes into the while loop, I need to remove that, but before removing I just grab it and then I do go to all of its neighbors. And check if there was some node which after the removal of this parent gives me an in degree of 0. So as soon as the in degree bit becomes 0 for any node, it means that it is valid to consider that particular vertex in our queue. Now suppose we have 5, 6, 7 as our microservices, and then we have 10 over here, right? And there is this kind of a dependency. So for 10 to be working, we need that 5th, 6th and 7th microservices all should be running and all should give their data to 10 before 10 can process anything out, right? So over here what can we say? That as soon as I visited 5, I will remove this in degree for 10. As soon as 6 gives the answer, it will remove its in degree. 7 gives the answer, it will remove its in degree. So every node has the responsibility of removing its in degree, which is contributing to the next of its neighbor when we are pushing it out. We are pushing it out of the queue. So that is what we are doing. Now we are guaranteed to know that if there is a node that will have in degree of 0 at some point, it is eligible to be pushed into my queue. So we'll push it into the queue, and this will carry on until we have reached the end of the topological sort and end of the BFS. Now there might be a case where there is a cycle or something where it will just come out of the loop and we won't have an in degree of like 0 anywhere. So suppose if there was 1, 2, 2, 2, 3 and then 2, 1. Now every in degree over here is 1. So there is no 0 in degree. Now no 0 in degree means my while loop will finish and then we'll be just returning an empty array. Empty array means, or else in some cases there might be a cycle at a later point in time. So suppose this kind of a thing. Over here we will know that 1 and 2 will go inside, but then after that it will be harder because I remove this in degree after visiting 1 as given here, but still again the problem arises that each of these will have in degree 1 and my list will be only with 1 in it, which will again be lesser than the number of vertices. If it is lesser than the number of vertices, if it is only equal to number of vertices, we know that it is a valid sort. If it is not, then we just return the empty array. This is how a cycle can also be formed. And one more thing to note is that we do not need any visited array over here, because we are doing a level order traversal, and we know that if I have visited some node, I will not visit it again ever, because it is first of all directed and I'm not going back. In the sense, if I visited U and I have completely visited it, when I go to V, its neighbor, I will not come back to U again ever in this BFS. So that is that. Coming to the DFS implementation, which might not be very intuitive, but yeah, we can just take a look at it. What over here happens is, like, if this was my graph, then in the DFS way, I will just either go to this completely, and over here I will push into the stack. 12 will be pushed, and then I will go to 13 and push 13, then come back to 7. Now I'll push 7. So now then again I'll come back to 5 in recursion, and then I'll push 5. So over here, if we consider this part, this is looking like, if we are popping it out into our answer, then we will have 5, 7, 13 and 12, which is our correct linear ordering, because what we are doing is we are pushing that element which is the farthest, in the sense the least, which has all the dependencies resolved. In the sense, only if this is the last element in the in our and last reachable element in the graph, right, then we know that all its dependencies are obviously sorted out, right? Only then we'll be able to reach it. If not, we wouldn't have been able to reach it also. So to remove something, right, to remove something, we need to first resolve all its dependencies. We are doing that only. And then to push it also, we need to go to all of its children, and then when we are coming back, then we are pushing it. So from 7 I pushed 12 and 13 first before going to push 7 in the stack. In the sense, first I went to all of its children and I saw that everything was resolved in its children part, and then I resolved for 7. So this is basically wherein the DFS comes in. DFS is basically wherein we mark some node as visited as soon as we visit it, and then we run our DFS on its neighbors if that visited of that neighbor is not true. Now TopoSort DFS, what we needed to do, we just needed an extra thing which was known as our visited array and a stack to store the ordering, visited array to store the state of the traversal. Now when we are popping it out of the stack and pushing it into the answer, it is in the correct order that we wanted. So I hope when I look at this video later on in some point in time, it will be like beneficial for me also, and it help someone out there maybe. Thanks.